Hi guys, so this class is about the oxidative phosphorylation step. The chapter is 19 of the book. This step is, let's say, the last step of the respiration, where you have the carbohydrates and you can also have lipids or amino acids feeding this respiration. And they are used to produce NADH and FDH2, sorry. That's going to be used as substrates in the electron transport chain. Okay, so all of this is going to be used to produce ATP. Okay, so ATP is the final product of this respiration. But remember that respiration is not only, we are not only talking about ATP synthesis. Respiration, especially the TCA cycling glycolysis, can provide substrate for many other pathways, metabolic pathways. So we have already discussed a bit about the difference between the oxidative phosphorylation that occurs in the mitochondria and the photophosphorylation that occurs in the chloroplast, right? What is the main difference? The substrates and the dependence or not of light. Photophosphorylation needs light, okay? Photo, light. And here, water is the source of electrons, so everything starts with the degradation of water, which is induced by light, right? Then you have many compounds that can accept the electrons and also transfer the electrons. At the end, you have two common mechanisms, which is the proton gradient that is created between one membrane in the chloroplast and also in the mitochondria. But the difference is what release these electrons with what release these protons. Okay, the proteins that compose the electron transport chain they are different between chloroplast and mitochondria, but they are doing more or less the same. Okay, so they are carrying electrons to one protein to the other, and also pumping protons to one side of the other of the membrane. Okay, and the ATP synthesized in a very similar way. So the protons that are pumped from one side to the other side of the membrane, the ATP synthase take this proton and pump back to the other side. So then you have ATP synthesis. So the ATP synthesis is very similar. What is different is the components of the system. Okay. So in phosphorylation we have water, and here you have NADH and also FDH2 that is going to be degraded by different complexes. The NADH by the complex 1 and the FDH2 is by the complex 2 in the respiratory chain. Okay, so here oxygen is produced by the photophosphorylation and the photosynthesis, and here the oxygen is the ultimate electron acceptor, so it's taking electrons. Okay, we are going to see that in plants, if you have, not only in plants, but you have overaccumulation of oxygen, this oxygen can become a reactive oxygen species, which is very bad for the cell in high concentrations. Okay, so we call this as ROS, reactive oxygen species. Is very when this kind of oxygen species over accumulate, it's dangerous for the cell in any case. And in plants, this is especially severe because plants cannot move, they are sessile, so they are under stress more often. So plants has one enzyme that can avoid this kind of over accumulation in the mitochondria. We are going to see this. And then at the end you have ADP being phosphorylated, and then you have ATP synthesis. So oxidative phosphorylation and photophosphorylation, they are very similar process, but with some particularities. So you have here the complex 1, the complex 2, the complex 3, the complex 4. In plants, we are going to have this AOX, which is alternative respiratory pathway. Instead of the electrons from the ubiquinone pass through the complex 3 and then cytochrome C and complex 4, you have the AOX. AOX can take electrons from this and reduce oxygen to water. So this is what AOX is doing. Okay. So here you have the matrix, the inner membrane space, inner membrane, and here the intermembrane space. Okay, so everything here is in the mitochondria. We saw a slide that many dehydrogenases can produce NADH and also NADPH, so these are substrates of complex 1. Okay, complex 2 use succinate, and all of this is gonna feed the pool of ubiquinone that can transfer the electrons to the complex 3, and cytochrome C can take electrons here to complex 4, and then you have the ATP synthase that's gonna synthesize ATP. So this is a summary of the electron transfer flow in the respiratory chain. So we can say electron transport chain or electron flow chain or many other ways. I prefer to use transport chain, but it's okay if you prefer to use another nomenclature. So you see here that these complexes are very huge, very big. So it's not only a single protein. You have in each color here you have a subunit. So it's very complicated to build in silico, let's say, if you want to build by yourself. So it's a very big protein, and of course it's also difficult to understand. This is the complex 1, this is the complex 2, complex 3, and complex 4. So you see how big they are. The most important message here is that the complex 1 and the complex 3, they are good pumpers. So they are pumping protons from the matrix to the intermembrane space here, you see? So 2 protons here by the complex 4, 4 protons here by the complex 3, and 4 protons here by the complex 1. Of course, depends on the amount of substrate that is being consumed. So you have here NADH that produce electrons and then pass through this quinone pool, and this quinone is passing through the complex, and then you have protons being pumped, and these protons is going to be dissipated by the ATP synthase. So this is the proton motif first that we say. So there's protons pumped from the matrix to the complex to the intermembrane space. This is very important, and remember this is very similar to the chloroplast. What is different here? In the chloroplast you have different proteins. Here you have these proteins here, complex 1, 2, 3, 4, and remember in the chloroplast you have photosystem 1, 2, and cytochrome B6F, plastocyanin. Plastocyanin is doing the chloroplast what cytochrome C is doing here, so transfer electrons to one complex to the other. Okay, so in general we say the ATP synthesis depends on the proton gradient, which is in the chloroplast, in the mitochondria, created by different complexes, but the mechanism is more or less the same. Okay, because you have this gradient created in the intermembrane space, and then you have ATP synthase here, and this ATP synthase take the protons from here and dissipate to the matrix again. So you have protons coming from the matrix to the intermembrane space by this complex, except the complex 2, and then ATP synthase is dissipating. So this mechanism is very dynamic. So you have protons coming from one side to another side, and then ATP synthase is dissipating. And this we call this as chemiosmotic model for ATP synthesis, which is similar, very similar between chloroplast and also mitochondria. Okay, this model supports this synthesis of ATP. At the end, we have a lot of ATP being produced by oxidation of just a single molecule of glucose. For example, we have 30 or 32 ATP being synthesized by one single molecule of glucose. Okay, because all these steps here, glycolysis, pyruvate oxidation, a TCA cycle, and also the acetyl-CoA, so this is the TCA cycle. You have here not directly ATP production, but 2 NADH can produce 3 or 5 ATP. Okay, so the glycolysis produce 2 ATP, but produce more 2 NADH, that if this is used in the oxidative phosphorylation, you can have from 3 to 5 ATP synthesized. Okay, so in the TCA cycle have 6 NADH being produced, which can produce 15 ATP. Okay, so this number here is if everything that is produced in glycolysis and pyruvate oxidation and also TCA cycle is used by oxidative phosphorylation, but it's not always like that. Okay, so you see that, remember that intermediates of glycolysis and TCA cycle can leave the mitochondria to be used for the synthesis of amino acids and fatty acids and so on. So this is the maximum capacity of respiration to produce ATP based in one molecule of glucose. Okay, but you never be always like that, because you have intermediates being consumed by other pathways. Okay. The oxidative phosphorylation is subjected to the regulation of glycolysis and TCA cycle also, because if you have a block of the TCA cycle, of course you have less NADH being produced, and then you have less ATP being synthesized. Okay, so many of these compounds, for example, if you have overproduction of ATP, you have block of many reactions. You see here when you have this red signal here, it's a negative regulator. When you have the triangle in green, you have a positive regulator. So when you have more ADP than ATP, you have these reactions occurring from citrate to isocitrate to aconitate to isocitrate, and then alpha cycloglutarate. Okay, but when you have overproduction of ATP by the oxidative phosphorylation, you see how many reactions here are blocked. So ATP is a kind of allosteric regulator of many steps in the glycolysis and also in the TCA cycle. Okay, so you see here in the glycolysis from glucose 6-phosphate to fructose 1,6-bisphosphate, the ATP can also block here. So if you have a lot of ATP being produced here, you can see that many reactions here is going to be inhibited. But then if you, for example, let's say that you have a lot of ATP being produced in your body, but you are not stop eating chocolate. You are eating chocolate a lot. So you don't stop taking glucose, but this ATP here is not necessary to produce anymore. So this reaction is going to be blocked, and this carbon here goes to somewhere else. Okay, for example, in the cases of citrate, instead of citrate or acetyl-CoA being used by the respiration, it's going to be used by the fat acid pathway. So it means that if you have a lot of ATP being produced, which it can be in the case of excess of glucose intake, instead of respiring this glucose, you are going to synthesize fat acids. So you are going to get fat. Okay, so if you are taking glucose too much, burn it, remember. Okay, otherwise you have fatty acids being synthesized. Okay, so many points of allosteric regulation by ATP, ADP, NADH, NAD, and so on. In plants we have a different protein, which the name is alternative oxidase, because it's an alternative pathway of the respiration. So from the ubiquinone pool, usually you have the electrons coming from the ubiquinone to the complex 3, but here these electrons can also be taken by the AOX, and the AOX is going to convert oxygen to water. Okay, so this enzyme is very important, and it's regulated by different things in plants. So pyruvate, for example, is one activator of the AOX. If you have more pyruvate being produced and you have more AOX activity, so pyruvate is allosteric regulator. You know what is allosteric regulation, so you can search this about this kind of regulation. There is also genetic control, which means that is a transcriptional control. So this is allosteric control. Many hormones, or for example hydrogen peroxide, can also stimulate the expression of these genes, AOX1 and AOX2, and then you have more proteins. Okay, and also many other signals, citrate, singlet oxygen, nitric oxide, can also induce the expression of these enzymes. And also AOX is also regulated by thyrodoxine O1, so one kind of redox regulation. So this thyrodoxine can also regulate some enzymes of the TCA cycle and also AOX. So the AOX can be activated by redox regulation as well. And when this occurs, so when you have overproduction of oxygen, you can have this kind of nitro and also overproduction of oxygen and nitrogen molecules. You can have these ROS compounds, which are very dangerous for the cell. So this occurs when you have abiotic or biotic stress. Okay, so in this situation, instead of the electrons going to the complex tree, AOX is taking these electrons to avoid the overproduction of oxygen. Okay, the overproduction of oxygen is very dangerous for the cell, and this enzyme is taking these electrons and then it's converting oxygen to water. Okay, so converting oxygen to water, you avoid these kind of molecules here that can be dangerous for the cell. Okay, so take home message. Oxidative phosphorylation is the major ATP producer in animals. So animals don't have chloroplast, right? So mitochondrial oxidative phosphorylation is the major site of ATP production. It involves different complexes in the inner membrane of the mitochondria. You see that the complexes are very big, and you are going to see in the next legs that is even more complicated because they created some metabolite channels. It's regulated by different mechanisms, by mainly allosteric regulation, by ATP, ADP, NAD, NADH, but also redox regulation. Again, the NAD produced in the previous steps in glycolysis and TCA cycle are used as substrate for the complex 1. The main difference about oxidative phosphorylation of the photophosphorylation is that oxidative phosphorylation don't need light. Okay, photosynthesis depends on light to create this energy. Light is the energy source. Here not. The energy source is NADH, succinate, and so on. So, as in the chloroplast, the ATP synthesis here follow a chemiosmotic mechanism where you have pumping of protons from one side to the other side of the membrane, and then you have ATP being synthesized by the ATP synthase. Okay. And last, AOX, alternative oxidation, is an important alternative respiratory pathway in plants, which avoids the overproduction of ROS species. Okay, so this is the class about oxidative phosphorylation. The next class, we are going to just specifically talk about some complex, and I will give you some new concepts about metabolite channels and metabolomes. Okay, bye bye.